Okay. So yeah, as Steven mentioned, I did my PhD at Harvard, and then I did a postdoc with Steven, and we work on like meta surfaces, inverse design, and so forth. And today I'm going to share with you some of my some of the work that we did on the end-to-end understanding inverse design, which I'll explain shortly. And basically, this is about like trying to acquire large volumes of data in the shortest possible time with like the smallest possible devices, kind of like how you can leverage nanophotonics and Maxwell equations and inverse design technologies to develop such devices, basically. So so think about it. These days, as we all know, I mean, everything is about data, right? And here I'm talking about that your social media data, which is of course incredibly important. But I'm more like, for research, I'm talking more about like the data of the physical world. I mean, especially the data that is carried by the electromagnetic waves, right? So if you think about it, right? I mean, a full electromagnetic image of the world is not just a 2D image, right? It has a depth information, right? But also it has a wavelength information, right? At each spatial point, and on top of that, it can also have the polarization information. So what we really care about is actually, comprehensively is a multidimensional data cube that we want to acquire, right? Electromagnetically. Of course, what are you going to use it for? The list is literally endless, starting from like medical diagnostics, robotics, all kinds of monitoring and surveillance and imaging techniques. And these like data, like multidimensional data are extremely important. So the question is, how do you acquire them efficiently, right? So so there are like these established techniques such as like hyperspectral imaging, 3D imaging, and you can do both at the same time. But the key here is that the most high performance setups to acquire these multidimensional data up to date, they are really bulky. For example, like if you want to acquire a hyperspectral data, not just a 2D image, but also like spectral information at each pixel, you have to use like a bunch of like lenses, coded apertures, wavelength splitters and dispersers and all of them. And like the more you want to acquire, the more complicated, the heavier, the bulkier your setup becomes. And it's even more challenging if you want to acquire not only spectral data, but also depth data, like a hyperspectral depth imaging. So one example that is really recent is you really have to like put together two bulky setups to be able to acquire these data at in a single shot. So the point here is really is like the complexity of the experiments. The measurement devices is really like unwieldy and like not good for like all kinds of situations. So the question that really motivated us is really, can we really get rid of all these bulk? And I have to remind you that why do you need all these like bulky, setups to do these kinds of tests? Because when you are using like traditional optical elements, most of these are designed based on ray optics, right? You draw ray diagrams, like complex ray diagrams, fine, but still you are actually using an approximation of the Maxwell equations that is not really, fully exploiting the full Maxwell equation. So, so the main question that really motivates us is like, can we really get rid of all of this bulk? Meaning, all these designs, that is coming from the ray optics approximation, by really exploiting the full wave Maxwell equations through the inverse designs. and try to really leverage Maxwell equations at their finest and at their best form, actually, right? So yeah, so this leads us to what we call the end-to-end nanophotonics inverse design, and then I'll try to go through that slide a bit slower. So what do we need to actually measure these multidimensional data, hyperspectral depth and polarization imaging all at once? So you definitely need a front end, a physical front end, right? But you also need like a signal processing backend, right? Because it is always the case that you cannot really make use of the raw image that you measure. So you always have to do like some signal processing. Now the key here is that we are going to actually simulate the entire pipeline, which is the physical front end and the signal processing backend from end to end, okay? And the physical front end is not gonna be lenses, mirrors, not ray optics elements, but really the full wave Maxwell equations where we know how to do inverse design, right? And such as topology optimization, for example, right? And what we are going to do is we're going to actually, cascade or couple, right, the front and the back end in a single pipeline and simulate the entire pipeline from end to end. And then we're going to actually run the the data acquisition process up until the final reconstruction of the data that we want. And then we're going to minimize the reconstruction error from the very final output all the way to the parameters of the of the physical front end. And here as the front end can be like a fully free from geometry as a topology optimization. So and here one thing that we really want to emphasize is that we are really going to back propagate the gradients, right? From the very end loss function to the very front end with all the physical parameters that we care about. And I want to mention that this is, this end-to-end strategy has already been demonstrated by a group at Stanford, but so far that has been done only using like a diffractive elements, which is actually not the full Maxwell equations, kind of like a ray optics approximation. So really combining the signal processing backend and the physical front end together in a single pipeline. So here's kind of like a much more precise formulation of what we mean by this end-to-end inverse design. So basically, what you have is a loss function, right? So which is the difference between the object that you want to reconstruct, the actual ground truth, minus the reconstructed object. And the reconstructed object is something that you actually obtain from solving a reconstruction problem in the backend, right? The signal processing backend. And in that reconstruction problem, what we have to do is we have to minimize data fitting time, which is the which is a model of how your image is formed on the CCD sensor, right? Given the nanophotonics that you have, plus some regularization term that I'll explain shortly a bit later, and then of course the image is formed in the linear regime. At least is given by like V equal to GU. V is the image. G encodes the nanophotonics part, right? The response of the nanophotonics front end. U is the ground truth that you want to reconstruct, and of course. And no image that you measure on your CCD is ever noise-free. So there is always going to be some noise that you have to include in your simulations. So here, the key ingredient is, of course, this G, what we call the measurement matrix, right? Which is nothing but the intensity pattern, right, on your CCD sensor in response to like test sources, right? You want to test like this point source with this wavelength and this polarization, what kind of pattern it gives on the sensor, right? That's a point spread function, and the image of the ground truth is basically, right, is a superposition of these like point spread functions. So this is basically like the image formation model, and G is of course given by the solving the Maxwell equations, because the front end is fully nanophotonics. Now, as I said, when you are actually solving this this reconstruction problem, usually this problem is mathematically ill-posed, meaning inverting, right? Inverting this equation is not always lead to like a stable same answer because of price. So what you do is you usually want to try to actually incorporate prior information about the nature of the object that you want to reconstruct, and that is actually encoded in this term actually. So so usually we look at like these kind of like a constraint, so to speak, basically the L1 regularization or the L2 regularization, and what they test is that they try to enforce things like sparsity, the smoothness of the reconstructed solution, and etc., kind of like a noise robustness, those kinds of features into the reconstructed solution. For example, if you only have the L2 term, we call it Tikhonov regularization, and in particular, it has like a closed form solution, such as this one, which is kind of nice. But in more general terms, you have to actually solve, you have to iteratively solve this minimization problem, which is nested, if you remember, within the solving the minimization of L actually. So this is a bi-level optimization problem that we are formulating actually. Okay, and here, as I said, this is all about backpropagating the gradients of L, right, with respect to P and alpha. Alpha is in the back end all the way to like a P and alpha, right? So, but here I'm not really actually writing down the explicit expressions for these gradients. Why? Because they are, first of all, very complicated and kind of like, really not very informative. On the other hand, we are really actually trying to like efficiently implement this backpropagation. And that is possible because of two things, right? First, we have these like a very advanced automatic differentiation environments that we could customize, and within that we have like our own like a custom in-house adjoint solvers in Meep, and also like the adjoint solvers for this kind of like a backend and all that stuff, and all of that actually come together and combined to make sure that we can do this backpropagation quite efficiently actually. So yeah, so so now I just want to like dig a bit about this. How do you construct this measurement matrix G? Because this is kind of like quite important. So this measurement matrix G is, as I said, is kind of like a conceptually straightforward to construct. What you do is you show like point sources one at a time, right? Do your nanophotonics front end, and you measure the intensity pattern on your CCD sensor, and what you and then you stack these point spread functions into a matrix form, and there you get your measurement matrix G. So what is the most important thing about this matrix actually? So when you actually try to do like try to do a reconstruction problem, you are, in essence, you are trying to invert the scattering process, right? So this is an inverse scattering problem, and in those problems, what you care about is something called the condition number, right? Which is basically how sensitive, right, is your reconstruction to small perturbations in your measurements, right? I mean, if your measurement is corrupted by some amount of noise, I mean, how much of that noise becomes amplified, right? Due to the inversion process. So that is given by the so-called condition number, which is, I mean, this expression, which is nothing else than like taking the ratio of like G inverse, etc. And the important thing is that you want to have this condition number, right, smaller, in the sense that if you are like a 10x smaller condition number, I mean, you can have your measurement setup more sensitive. I mean, more robust to rise by 10 times, for example, actually. So one thing that we started to apply this end-to-end info design strategy is to really try to exploit the full Maxwell equations in terms of like data acquisition problems. So one thing that the full Maxwell equations really shine, right? I mean, when you talk about like the sensing and like imaging problems is when you have to acquire polarization information, for example, right? So for example, like, I mean, you have a fluorescent molecule, right? Which has an instantaneous dipole moment, which can be, I mean, fluctuating, right? But with all the like all kinds of sensors, what you can measure is only a time average intensities. So what you really care about is the coherences, right, of this of this polarization. Basically, what you can measure is something called the coherence matrix, which is kind of like the actual intensities in the X, Y, and Z axis, and also the correlations between all these components. And you can think of it simply as a 3D generalization of the familiar 4 Stokes parameters that people routinely measure in polarimetry, right? So we use the end-to-end formulation to try to design a very compact device, right, which can actually extract, which can actually measure the full coherence matrix of a fluorescent molecule, for example. But I mean, it doesn't have to be just the polarization information, right? I mean, it can, it can also have, it can also extract the spatial information, the spectral information, and going back to the like a multidimensional data that we really want to extract. So let's like proof of concept. How would you actually design these compact devices to actually extract spatial, spectral, and polarization information all at once from a single monochrome image, basically. So yeah, so this is the result of our end-to-end info design method. So basically what we're optimizing is 4 layers of free-form geometry. So all the layers are altogether only like a 4.5 micron thick, so which is really compact compared to like a centimeters. Compared to like a several centimeters of like a lenses and mirrors and whatnot, right? So this is like a fully non-photonic, like a 4.5 micron thick, ultra compact structure. And in each layer, the degrees of freedom are basically the variable height layers. So what we have is we had a 3D printing in our mind, so that this kind of geometry is kind of like a compatible to like a 3D printing. So the material that we used was actually like a 3D printable polymer. So the index of 1.5 is not a very high index, but still, the kind of geometrical complexity that you can take advantage of when you really go down to the Maxwell equations and like inverse design it is like such that it can really do like a very complex test, such as extracting spatial, spectral, and polarization information all at once, right? So here we minimize the mean square error, which is the loss function that I mentioned before, but at the same time we also monitor the condition number of this structure, right? I mean, the inverse condition number of this structure. And you can see that as the mean square error is reduced, right? And the condition number of the measurement matrix actually is also reduced. And it's reduced so much so that, I mean, the final number that we got was actually 6.4. And remember that your condition number cannot be smaller than 1. So actually it is now actually about the same order as the smallest possible you can get. And the most important thing is that, sure, I mean, this structure looks like random, and what if you just replace this entire, I mean, crazy structure with just a randomized, a structure? Actually, we tried that, and what we found is that for a randomized structure, I mean, the condition number that you will get for this reconstruction process is actually 10 times higher. And if there's like nothing in here, just like just free space or like a uniform structure, the condition number of the reconstruction process is 100 times higher, which means that you can no longer reconstruct actually match, because your inversion process is very sensitive to noise. But there is another important aspect. If you put a random structure or even a uniform structure, I mean, sure, I mean, if you put a random structure, there might be some kind of like a discriminating, discriminative scattering, so that that will help with the reconstruction process. But on the other hand, in contrast to the optimized structure, there is a little bit of focusing action that becomes optimized in the Endtoend design. So what we really found is that in addition to the improvements that, one order of magnitude improvement in the condition number, you are also getting 3 times more transmission, more throughput, right? Compared to the random or even uniform structure. Because if there is nothing here, the light from these point sources, just like these are high ending, right? So they just spread out actually. So but in the presence of this structure, this actually has a focusing action. It turns out that it is actually doing, it is actually leading to like a 3 times more transmission throughput than random or even uniform structures. So actually the improvement is so twofold actually. Not only the improvement in the in the condition number, but also due to the improvement in the transmission, which is very important because now you can also try to image acquire these data in the low light condition, for example, right? And in passing, I also want to mention that there is also a paper that that tries to actually bound what is the absolute minimum condition number you can get for these kinds of like reconstruction processes, and they found that they didn't find any structure, but just the bounds of like a theoretical bounds of like whatever structure you could come up with, you cannot go below this number, and it turns out that that number is actually around 6. And it's really remarkable that this Endtoend inverse design is really approaching the best possible performance in this context. So what we show before is basically kind of like a proof of principle, like how do you design like extremely compact devices through the Maxwell equations for spatial spectral and polarization information extraction. So what we eventually want to do is really try to do like a multidimensional imaging, right? From a single monochrome image, you want to actually extract the full multidimensional data cube that I mentioned before. So this is kind of like the first step, I would say. We have been able to like scale up this kind of like fully freeform inverse design to areas of 1 millimeters or 2 centimeters or stuff like that. But on the other hand, we already have like a technology to inverse design like regular metal surfaces, right? And so so we did that in an Endtoend framework, and we come up with like some interesting design which can actually extract 2 depth information right? And two wavelength information and four polarization information, and at the same time image this data cube actually. So so with that, I mean, I just like to see a few things about the implementation. As I mentioned, this is all done within a customizable automatic differentiable environment, but modified, I mean, critically modified with the efficient solvers and Meep solvers and forward and adjoint solvers, and kind of like put together to, I mean, to be able to like make it scalable to like a larger and larger structures. So so right now the code is not exactly user friendly, but if you want to play around with it, I mean, for the purpose of like I mean, to do any end-to-end like design problems, I've given the link here. And on the other hand, I mean, looking forward, what we are trying to do is to really like, I mean, scale up these designs, right? I mean, these end-to-end optimized designs to larger and larger apertures and larger resolutions, and also like a much more compact form, and do like do the multidimensional imaging. So with that, I would like to acknowledge, of course, Stephen, my advisor, and also our collaborators, Marin and Arca, and also Charles from Marin's group, and also the funding agencies that have supported this work so far. Okay, so with that, I open the floor to questions. Yeah, so there is one question that I just could see. It says, did you use nanoscribe 2 photon printer? Yes, not particularly for this structure, but we are actually have like some other designs that we are using to fabricate with nanoscribe. Yes, so there are limitations to that, because I mean, the resolution that we can go with nanoscribe right now is like 300 nanometers. But looking forward, I mean, we are also looking towards like things like multi-step lithography, right? Which is just deposit etch planarization and deposit etch, those kinds of fabrication actually also. So.
Artavano Skui here.
Oh yeah.
I didn't quite understand why the condition number improves. Is that intentional, or is that like an accidental byproduct of your design? Like why would you expect the condition number to go down along with the mean squared error?
That's an excellent question, actually. We are not intentionally minimizing the condition number, but on the other hand, I mean, what we found empirically, at least, is that when you actually minimize the mean square error, but the reconstruction process is done with the Tikhonov regularization with this like, with some choice of alpha. You can see that, I mean, if when the mean square error of such reconstruction goes down at the same time, and always actually go, the condition number actually goes down. So if you want to dig a little bit deeper, there are actually deeper connections of this expression to the to the condition number of the of G actually. So not very direct, but like you can actually like dig into like a statistical literature of like an inverse scattering, where you will see that Tikhonov regularization is kind of like the best form of like a linear inverse scattering process, and it can kind of like affect the condition number in the sense that it is most noise robust actually. So intuitively, what you are doing with the Tikhonov is also try to make your reconstruction process robust against noise, right? That's your prior information. You are saying that some perturbation in the measurement cannot lead to like big changes in the reconstruction. That's what is being enforced by the Tikhonov. So so it is so as it turns out, when the G improves due to the Tikhonov reconstruction, and during the info design process, it actually also always actually leads to like a reduction of the condition number actually. Yeah. So if that answers your question. So there's another question that yes. So that's how does this depend on the sparsity of the ground?
Zin, could you just read the question again so everybody's aware what it is?
Oh sure. So this question is asked by Wade. He's asking, how does this depend on the sparsity of the ground truth? That's a very good question, actually. So I didn't go very deep into like these, sparsity and stuff like that. That's, the example that I show, the example that I show here, right, is a reconstruction process that is using Tikhonov regularization, which is usually used to solve like determined or overdetermined problems. I mean, it can be used to solve like underdetermined problems, but more suitable for like overdetermined problems, meaning like your U has a much smaller like at least equal dimension as the V that you measure actually. So so in these cases, right? I mean, and in the problems that I show you, we are not really enforcing any sparsity condition. On the other hand, we actually had done like problems that are underdetermined problems, meaning you want to reconstruct a U that is a much larger size than the V, the image that you are measuring. So like a small number of pixels, but you want to reconstruct a huge, a huge object, for example. That's underdetermined. So for those kinds of problems, what we actually used was compressed sensing, right? Basically, you have to impose, right? This L110 actually. So what we found is that, remarkably, what we found is that with this end-to-end inference design, when we actually implement this compressed sensing reconstruction in the backend, the kind of like a physical structure that it comes up with actually matches the theoretical limits of the compressed sensing performance. So to be precise, compressed sensing says that in order, the best possible, right, measurement matrix that that will perform with compressed sensing is basically something that has the restricted isometry property, which is basically kind of like a you can get like a Gaussian matrices, right? Random Gaussian matrices. But you have to realize that a random Gaussian matrices doesn't really mean a random structure actually. And if you just put a random structure, you will find that your measurement matrix G actually leads to like a very, non-random, BSF. But as it turns out that when we do the end-to-end info design, it actually comes up with like these physical structures with measurement matrix, which actually can match the performance of the compressed sensing optimal, CS optimal, right? RIP matrices actually. So which means that we are actually try to exploit the sparsity, as best as it can, as the current theory allows for, right? And because like, when it comes to sparsity, the most, to my best knowledge, the most understanding is comes from the compressed sensing, right? So that's what we found actually. So if, so hopefully that answers your question.